All right, so now let's talk a little bit about big, little in detail and why ARM decided to do big, little. So here are the details of it. Here are ARM's pictures of it. Here's the picture of the little processor. You can see it's a lot smaller. It doesn't have so many things going on it. Here's the big processor, and the big processor has an awful lot of stuff going on it. So the little processor is simple. It has fewer of these functional units that do different things. It's only got 5 of them in this case. The big processor has more of these, and it has something special called out-of-order execution. So you've got 8 of these functional units. In particular, if you look up here in the little processor, we had 1 integer unit, but down here in the big processor, we have 2 integer units. So it can do work twice as fast, twice as many integer things at the same time. You also look at these and you'll see they have different lengths. So the big processor is really long. It has 24 stages to compute the work. Whereas the little processor is much shorter. It has 10 pipeline stages between starting and getting the work done. So all of these things here, this is computer architecture. And by the time you're done with this class, you'll understand the trade-offs in pipeline lengths. You'll understand the issue of having multiple things going on here and what all of these stages are. And you'll understand what a whole bunch of these different units are. So this is the sort of thing you're going to learn about in this class. Now, we showed why they might want to do this or how the details of this. But there's a good question, how can they afford to do this? So how can they afford to just put 2 different types of processors on their chip at the same time? So let's take a look at the relative sizes of processors over time. So this is how big a processor was back in 1995. If we move forwards a little bit, we can see that the processors got a lot bigger. Well, they didn't get bigger. What happened was the transistors got smaller, so you could fit more stuff into the same area. So in 2001, we had this many transistors to play with. And if you compare this to 1995, what you can see is that in 2001 you could fit a whole 1995 transistor just in the corner. And this kept growing and growing. So by the time we get up to 2005, you could fit a whole 1995 processor, everything on the processor in this one little corner of a 2005 processor. And this is because the transistors got so much smaller. So what ARM has said is, hey, we're going to put 2 different types of processors on there. And how can they do this? Because transistors got smaller. They've got lots and lots of transistors to build with. Here's another example of this. Here's a picture of ARM's very first processor, and here inside this circle is the size of ARM's smallest processor today. So ARM's smallest processor today is this teeny fraction of the size of their first processor, and that's because the transistors have gotten smaller and smaller and smaller. And it's not just ARM taking advantage of this. In 2012, Intel put 56 Pentium CPUs on one processor. This is their Intel Xeon Phi. And you can see transistors just got so small that they could put 56 of these on one processor, whereas 10 years earlier, they could only fit 1 on the processor. So when we ask the question, how can ARM do this big little thing? The answer is by scaling. You can put many, many more transistors on the same chip for the same cost. And so ARM has decided that they're going to use some of these transistors for a slower, low-power processor and some of the transistors for a faster processor. So now that's how they can do it. Let's talk about why they should do it. And so here we're going to look at trends in processors. So here we've got time from 1985 to 2010, and on the side here we've got a logarithmic scale. We're going to look at a bunch of things here. So the first one here, this is number of transistors. So this is what's known as Moore's law. It's a linear line on a logarithmic scale. So you can see what's happening. This is exponential growth. This says every 18 months the number of transistors we have doubles. And that's what we just showed you on the previous slide. Now let's take a look at the relative performance. So the relative performance kept going up and up and up, just like the size of the number of transistors, until about 2003, 2004. And at this point it's slowed dramatically and hasn't gone up nearly as much. Let's look at the clock speed. So again, the clock speed was also going up dramatically, and then in 2003, 2004, it got flat. Didn't go up anymore. We're stuck at the same speed of chips we had before. The question is, why did this happen? Well, to understand this, we need to look at the next one here. This is power. So here's the power of the chips, keeps increasing and increasing, and then right here in 2003, 2004, something happened. We reached what's known as the power wall. And at the power wall, these chips were so hot that we couldn't afford to cool them. If we continued this line up here, we'd be paying more to cool off our chips than we'd be paying to use our chips. So they had to stop making the chips hotter and hotter, and the way they did that was by stopping increasing the clock speed. But while they didn't make them faster and they didn't make them hotter, they still kept getting more and more transistors. So to get better performance, what they did with all these extra transistors they were getting was they went and increased the number of cores. So this is why we got multi-cores starting in 2003 or 2004, because we'd run into the power wall. We couldn't get better performance by making the chips faster because it used too much heat. So instead, they didn't make them faster, they just put more processor cores on the same chip. So why should ARM do this? Well, the answer is they can't get more performance because they're limited by power, but they've still got more transistors, so they should use those transistors to get more efficiency. So by having processors optimized for efficiency, they can use those transistors in a good way. All right, so here's a question about the trends in computers. Which fundamental changes happened to computer processors in about 2003? Well, the answer here is all of these. In about 2003, the clock speed stopped going up. You can see that here. The chips got too hot to cool. That's why the power didn't go up. That's what forced them to stop the clock speed. And at the same time, they still kept getting more and more transistors, but couldn't run them faster, so designers started increasing the number of cores and making multi-core processors. So all these changes happened in about 2003. Now we talked about what ARM is doing with Big Little, but they're not the only players out there. What are other people doing? So if we look at graphics processors, or GPUs, you can see they're made up of lots and lots of very small cores. So they can be very power efficient if you use all of these cores because they're small, reasonably power efficient cores. Another thing is heterogeneous computing. This is the idea you combine two different types, small cores and big cores, but here we're combining CPU big cores and GPU little cores. So this is somewhat like ARM's big and little, but these are different types of cores. ARM's cores were the same type of core, just different versions of them. Here these are very different cores. We have graphics cores and we have CPU cores. So in all of these cases, the reason they're doing this is for power efficiency. You can't get any more power out of your chip because you can't afford to cool it, so you have to figure out a way to build chips which are better at their use of the power. So this should have given you a pretty good overview of what computer architecture is. It's understanding these details, how they relate to performance and power, understanding why you'd have these different trends, and how architectures are built. So power and performance, design trade-offs, and building the hardware. And there's one important thing to remember. It's also about making it programmable. Many people have designed incredibly fast computers that nobody can program, and they're not very successful when that happens. So why should you care about computer architecture? After all, you're probably not going to go off and get a job designing chips. And the reason is computers are evolving fast. If you understand what's going on inside them, you have a better idea of understanding how they're changing and what that means for you. So this architecture is critical for power efficiency, and it's not just about designing hardware. Think about if you're going to go out and you're going to write a cell phone program and you want to sell it. Well, now you're selling it to cell phones that have these big little processors in them. What does this mean about writing your code? Should you change the way you write your program to take advantage of big little to get better battery life for your users? Or maybe if you have CPUs and GPUs together, should you change your software to take advantage of this? So understanding these trade-offs is important for you if you're going to go off and write software. Plus, it's fun. And not only is this a good challenge, but they're hard problems, smart people, and lots of money. This is, $100 billion industry, so lots of really smart people are thinking really hard about these problems, and that makes for a lot of excitement.